Okay. All right. Well, happy Friday and happy end of eighth week. So just a couple weeks left, ninth and 10th week. And they go. I always feel like those last couple weeks go by quick. But let's go ahead and take a look at today's lecture. So today's lecture is a little bit of it's going to be a bit of a review lecture. So one of the prereqs for this class is Stats 10 or equivalent, and many of you, well, and also just generally speaking for the entire class of 80 students who are enrolled, but many did not actually take Stats 10 here at UCLA. Some of you did, or something equivalent, but many got credit for like AP Stats or something of the sort. And so I just wanted to spend a little bit of time just reviewing some key concepts from kind of intro stats. And so this one lecture today I've titled Review of Statistical Inference, and it's going to be kind of like trying to fit all of Stats 10 or all of AP Stats into one lecture here, just to make sure we're all kind of on the same page as far as how do we define a p-value, and how do we what happens when we do statistical inference, when we do a hypothesis test, and all of that. So let's take a look. Okay, so first of all, how do we probably the very first thing that you cover in your intro stats class is something that you already knew prior to your intro stats class, which was like, what's the median and what's the mean, right? And I think you probably learned those things, I don't know, fourth grade or something, like in grade school. And oftentimes the mean is just presented as like, okay, this is what it means to get the average. And the way you do it is you add up your numbers and you divide by how many you have. And we always, the mean has always been presented as kind of just this formula. I don't know if anybody presents the mean like intuitively. What does it mean for you to have this average? What does that thing do? And both the median is like kind of, you start on the ends, you put them in order, you start on the ends and you work your way and you kind of arrive at the median. And what are these things doing? These things are basically finding balance points in your data. And the median, you can think of as the median is the location that balances the number of points that you have that are above the median and below the median, okay? And the mean is the location that balances the deviations above and below the mean, okay? And so because the mean balances the deviations, it gets pulled in the direction of skew. So like if you have these outliers, the mean gets pulled in that direction because it's trying to balance the deviations. And so here's a little picture. Let's say you have these 6 data points, 1, 2, 3, 4, 10, and 10. Okay, where is the median? The median is between 3 and 4, and we often just pick 3.5 or something, exactly halfway in between those two center points. And that balances the number of points. You have 3 points below the median, and you have 3 points above the median. So that's kind of the sense of where we are balancing the points. The mean balances the deviations, and so where's the location where the deviations get balanced? So that's going to be at 5, and you do this by, you add up all of your numbers and you divide by how many you have. And so if you add these up, you get 30. 30 divided by 6 gives you 5. And you can see that, when you do that, the deviations for the points below the mean are, -1, -2, -3, and -4, okay? And those add up to -10. And then you have 2 points that are above the mean, and they both have deviations of +5 and +5. And so those also add up to, those add up to 10. So those are in balance, right? And if you try to pick any other location for this location, the deviations will not be balanced. And so that's kind of the idea of, the median and the mean, that they balance things, but they balance slightly different things. And then the next thing that you cover in descriptive statistics is this, what is the variance and standard deviation? You have other measures of spread, but these things basically measure, are your values very similar to each other? which means they exhibit little spread or low variance, or are your numbers, widely, they're quite different? And so the examples I like to use are, imagine a classroom of students, and what are the ages of the students in that classroom? So if you were to go to, say, an elementary school and visit a second grade classroom, and you look at all the students there, and you look at, ask, how old are you? All right. You're expecting a very narrow range of ages in second grade. At least in the U.S., it's based on age pretty much. And so everybody there is going to be like 7 years old, maybe an 8-year-old, but you're going to have very, very little spread. You're going to have, very little variance or variation in the values that you see. Okay. Whereas if you were to go to, say, the DMV or the doctor's office or something like that, and you ask, what is everyone's age? You're going to have all kinds of different numbers, right? You'll have, seniors in their 70s. You'll have middle-aged people in their 40s. You'll have some young adults, maybe some children, maybe even some babies. And so you'll have, kind of this very wide range or a high amount of variation. And the formula that we use often to kind of measure the variation is the variance, and we can think of the variance as the average of the squared deviation from the mean, right? So this picture is, what are the deviations from the mean? And we said, there's +5, +5, -1, -2, -3, -4. And the variance says, okay, take those deviations, let's square them, and then we'll get the average, okay? And then if you do that, you'll get the variance, and then if you take the square root of that, you get your standard deviation. And so the formula for the variance looks like this, and you can kind of think of building it up. You take each individual point, and you subtract off x bar, and that gives you, how far, what is the distance that point is from the mean, and then you square that distance, and you do this for every point, so you have, a bunch of squared distances from the mean. And then if we said, okay, take the average of all of these values, you would add them up, the summation over the I points, and divide by n. That would be the average squared distance from the mean. You guys took 100B, and I think you learned that this value is biased, right? And then, and if you do divide by n minus 1, this is the unbiased estimator for the average distance from the mean, and that's the variance. Do you guys learn why you do n minus 1? Other than, like, that makes it unbiased, but why? Like, intuitively, like, do we know why dividing by n minus 1? Why would dividing by n end up being biased? So it's known as Bessel's correction. And the thing is if you knew the population mean mu, if you knew this value, okay, if you knew this value and you took your points and you subtracted off mu and you squared that, and then you took the average, right? So you took, what is the distance each point is from mu, you square that, and then you average that, that would be unbiased, okay? If you did this for any kind of data set, of course, your estimator is going to be a little bit higher, a little bit lower, depending on which random sample you get. But in the long run, if you knew what the population mean mu is, and you said, okay, well, what is the distance from mu? Let's square it and then take the average. This would be unbiased, okay? But we don't have mu, so what do we use instead? We use x bar. X bar is basically the mean of your sample. And because this x bar is based on your sample, it's always going to be closer to the center of your sample than the actual mu is, right? So wherever the actual mu is, your x bar is always going to be in the closer to the center of your sample versus the actual value of mu. And so therefore, when you measure the distances from x bar, those distances are going to be less than, say, the distances from the true value of mu. And so taking the individual x's minus x bar is always going to underestimate the distances from xi minus mu, okay? So this is always going to underestimate this quantity, xi, basically, xi minus x bar is going to underestimate xi minus mu, and it turns out that to kind of compensate for that underestimation, okay, using this, all we have to do is divide by n minus 1, okay? And then I think in 100b you've proved this somewhere along the way, maybe not. Okay, but anyway, that's known as Bessel's correction. That corrects for underestimating the quantity there. So that's so you covered that, and then you know, in Stats 10 you move right along. You have all of these probability rules and things like that, and then somewhere we say, all right, now we're going to look at probability distributions, and here is the normal distribution, right? This is what it looks like, and we say this thing is unimodal and it is symmetric, and if your data follow a normal distribution, most of your values are near the middle. And you know, so your mean, the standard normal has a mean of 0. Most of your values are near 0. And as you go farther above or below, you get fewer and fewer of these things. And the normal distribution is, you know, kind of set up where, you know, once you're three standard deviations above the mean, these points are very, very, very rare. Okay. And so you have the empirical rule. Do we have these numbers memorized? 68, 95, 99.7 at 1, 2, 3. Okay, so you should, even if you have like open note tests, like you should have these 3 numbers memorized, at least for the normal distribution. So around 2/3, 68% are within plus or minus 1 standard deviation of the mean. 95% are within plus or minus 2 or 1.96, more accurately 1.96 standard deviations of the mean. And then 99.7 are within plus or minus 3 standard deviations of the mean. And so all to say is that, you know, if something is more than 2 standard deviations away from the mean, we consider that to be unusual. And if something's more than 3 standard deviations away from the mean, we say, you know, that's highly unusual. All right. Okay, so let me go ahead and give you your first view quiz answer. The letter E. E as in elephant. E as in elephant is your first view quiz answer. All right, so you have the normal distribution, and then we bring up, we want to do statistical inference. And statistical inference is the idea of trying to make a conclusion that applies to the population even if we didn't observe the population directly, right? We're only observing a sample, okay? So, you know, you have a research question, and the way we would answer the research question, you know, if we had unlimited resources, is we would find the population associated with the research question, and that population includes every person who is relevant to answering this question, right? But the problem is the population is always too big. It's too big for us to study directly, and we might not even know who's in the population, right? So if your question is, you know, is this new drug that we're developing, is it effective at treating some disease JKL, okay? The population there is everyone who has disease JKL. And everyone, there's probably too many people, and we don't even know, right? Part of the problem with a lot of diseases is people don't even know they have a particular disease until they start showing symptoms or something like that. And so there's no way for us to track down this population directly. So what do we do instead is, this is my beautiful artwork here. This potato is supposed to represent the giant population, okay? And from this population, we select individuals at random, and that form our sample, right? And so what we are able to study is this sample. So maybe our sample has 50 individuals selected, okay? Ideally, the 50 individuals that we've selected, or, you know, whoever we selected to be part of our sample, you know, whether it's 50 people or 5,000 people, ideally the sample we have is representative of the population, representative, kind of like a miniature version of the population, right? It's kind of, I don't know how to explain representative, but basically, you know, you want to kind of, the sample that you're looking at, you want it to be like almost like a little miniature, kind of a cross-sectional piece of the entire population that you could imagine, you know, like if you were able to just kind of duplicate this thing over and over again, it would end up looking something like the entire population. And if your sample is not representative, for example, you have too many of a particular group of people, okay, so, and it could be, you have too many old people or too many young people or too many of one gender or too many of a particular racial or ethnic group or something like that, or too few of another group of people or something, then your sample is not going to necessarily look like the population, okay? And so, this is just something we have to keep in mind, especially if we're reading studies and, the studies, are from, say, another country. So, let's say a study was done in China, then probably the people selected to be part of their sample are going to be more reflective of people in China than, say, people in the U.S. or some other part of the world, and therefore the conclusions may or may not be able to be generalized to other things, just because there's going to be differences, right? Changes, differences in diet, differences in genetic things could affect the results. So, ideally, whatever sample we're looking at is representative of this population, whatever that is. All right. Now, one method that should produce representative samples is random sampling, but because it's random, we have to keep in mind it's not guaranteed to produce a representative sample, right? It's random. So ideally, randomly we select people. Hopefully, they look kind of like the population, but again, because it's random, maybe you selected too many or too few of a particular group. When you select a random sample, you take your sample and then you often want to summarize the values in your random sample, and so you might calculate, say, the mean of that sample. Because the sampling process is random, though, if someone else were to do the same thing and take another random sample from the same population, the individuals that they select will be different from the individuals we selected. And so when they calculate the mean of their sample, they're going to get different values and a different sample mean. And the question is, what kind of different values are we going to see? All right, we're going to, some sample means are going to be more likely, other sample means are going to be less likely. And if we want to know, what's the distribution of all the different possible values of sample means, that's going to be what we call the sampling distribution of the mean. Sampling distribution of the mean. So hopefully this is all review here. And so this is kind of one way for us to simulate a sampling distribution via, or we can create a sampling distribution via simulation, right? And so we start off and we say, let's say we have some kind of population, and we'll specify what the population looks like. And so in this case, I'm going to say the population will be standard normal, so we'll have a mean of 0, standard deviation of 1, okay? But you could specify whatever population you want. What we'll do is we'll draw a random sample from that population, and we're going to calculate the mean. And then we're going to do this again. We're going to draw a different random sample from that population, same size, and calculate the mean of that other sample. And we're going to repeat this a whole bunch of times. Every single time, we'll take random samples and we'll calculate the sample mean. And then we're going to record every single sample mean we see, and we're going to look at the distribution of sample means. Right? And what's amazing is that if the sample size is large enough, then the sampling distribution of the mean will follow a normal distribution. And the standard deviation of that normal distribution will be sigma divided by the square root of n. And it's amazing because, in this example, I'm saying the population is normal, but even if the population does not have a normal shape, even if it's this really weird skewed shape or, multimodal thing, or even a kind of a dichotomous population, if your sample is large enough, the sampling distribution of the mean follows a normal distribution. So here's just an illustration. This is I drew a sample, I think of 10 values, or how many values did I draw? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, no, 16. 10, 11, 12, 13, 14, 15, 16. 16 values, right? And they are shown on this kind of this rug plot. These little red tick marks indicate where I've drawn values. And so I got, in order, I got negative 2.21, negative 0.84, negative 0.82, negative 0.63, negative 0.62. So these are actually two different dots, negative 0.31, negative 0.04, 0.18, 0.3, 0.18, 0.33, so on and so forth. Largest value I got was 1.6. And if I take the mean, what is the mean of all 16 of these values? The mean is 0.092, indicated with this red line. If I take another random sample of 16 values and I sort them from least to greatest, these are the values I get, from negative 2.31 to 1.98, and I get a mean of positive 0.096. Here's another set of 16 random values, and the mean of these values is negative 0.197. And so these are just a few slides indicating what different random samples of 16 might look like, okay? And so, when we look at these things, we see, oh yeah, most of the time my values are between 2 and negative 2, okay? And occasionally I'll get a value, farther away than two standard deviations, okay? But most of the time my values are between 2 and negative 2. And if I took enough samples, I would get some values above 3 or below negative 3. And so this is just to kind of show you what different random samples might look like along with their sample means. And what I can do is I can just kind of repeat that process, say 10,000 times, or I could have just as easily done 100,000 or a million. And so all I did is I just ran a for loop. I'm going to say, for I in basically 1 through 10,000, take 16 values from the normal distribution, 16 random values. So our norm will select random values from the normal distribution. That is going to form my random sample. And then what I'm going to do is I'm going to calculate the mean of those 16 values. And I'm going to store that mean into sample means location I. And I'm going to do this 10,000 times. And so at the end, sample means has 10,000 values. And I say, okay, what is the mean of all of those means? What is the mean of all 10,000 different sample means? And I get a value very, very close to 0, 0.0015. So that's going to give me a value very close to 0. And I ask, what is the standard deviation of all 10,000 of those different sample means that I have, right? So sample means is kind of a vector of 10,000 different sample means. And the standard deviation of all of those things is around 0.25, which is, in line with the central limit theorem, which says the answer should be sigma, which is 1, divided by the square root of 16. So 1 over 4 should be around 0.25. And that's what I get here. I can take a look at, I can create a histogram of the sample means. And indeed, I get something that looks a lot like the normal distribution. It's not perfectly so, just because, well, I only have 10,000 of these things. And so, if I were to draw a larger sample, we'll get something, law of large numbers, we'll get something that approaches the theoretic distribution more closely. But I'd say this is about as close as we'll get, on a practical basis here. And so here's a histogram with showing all of the different sample means that I've drawn here. Okay. I can draw a QQ plot, and what we see is that, yeah, these dots are almost, perfectly in a straight line. So basically, the theoretic quantiles and the sample quantiles that I got in my my points are close in alignment. And always, you might see a little bit of deviations from, in the end. And basically, we're just saying, yeah, we got a few more here than we might have expected. Or maybe not as many. I don't know. Okay, but we got this is what it shows here. Okay, so that's the kind of the summary of the central limit theorem, and that is that the mean of your random sample will come from a normal distribution, and the mean of that normal distribution is going to be mu, the population mean, and the standard deviation of the sampling distribution is sigma over the square root of n. We call that quantity the standard error, and we can see because n is in the denominator, as your sample size increases, your standard error is going to shrink, right? And also from this, we know the empirical rule says, if things follow the normal distribution, around 95% of the time, you have a 95% probability that whatever random value you draw from the normal distribution is going to be within 2 standard deviations of the mean, right? And so when you draw a random sample, we have assuming the central limit theorem is met, there's a 95% probability that the mean of the random sample will be within 2 standard deviations or 2 standard errors of the population mean. And we often use this as kind of our foundation for statistical inference. All right, let me go ahead and give you your second view quiz answer, which is the letter C. C as in cat is your second view quiz answer. C. All right, and so using that kind of key idea here, we create the confidence interval. So we said, okay, based on this, we know that the population mean is 0, and 95% of our random samples are going to be within 2 standard deviations of the population mean. So we can kind of reverse that, and we say, okay, whenever I see a sample mean, I can be 95% confident that the population mean is within 2 standard errors of it, right? So the central limit theorem says if you have a population mean here, 95% of the time your sample means are within 2 standard errors. So just the reverse is kind of flipped around. We can do the same. If I see my sample mean here, I could be 95% confident that the population mean is within 2 standard errors. Now, one problem is that we don't know what the standard error is exactly, okay? Because the standard error of the sampling distribution is sigma divided by the square root of n, right? And sigma is the population standard deviation. And so usually if you don't know what the population mean mu is, you're not going to know the population standard deviation sigma. So what do we do in this scenario? Well, what do we do here? Well, we say, you know what? I don't know what the population standard deviation is, but a reasonable estimate for using a reasonable estimate for the population standard deviation is our sample standard deviation. So we use S, the standard deviation of our sample, as an estimate for the population standard deviation. Okay, well, that's fine, but this introduces extra uncertainty. And so how do we compensate for this extra uncertainty? Well, instead of using 1.96 standard deviations, which comes from the normal distribution, we relax the normal distribution a little bit and we get the t-distribution. The t-distribution looks a lot like the normal distribution, but it's got heavier tails, it's wider, it's kind of like a stretched out or flattened out version of the normal distribution. And again, without getting into the math, that by using kind of this flattened out normal distribution, the t-distribution, that compensates for the extra uncertainty of using S as an estimate for sigma, your sample standard deviation S. When you use that as a guess for what sigma, your population standard deviation is, that changing it from 1.96 to something a little bit bigger makes for that, compensates for that. Did you learn about the history of the t-distribution? Like who made the t-distribution? It was developed by William Gossett, and his occupation was he was a quality control engineer at Guinness Brewery in Ireland, right? So you think of you go to what's the whatever. There's like an Irish pub in Westwood still, or no more. I don't know. Okay, well anyway, you can buy Guinness, right? And it's heavy beer. I don't know if anybody drinks, but anyway, he was this quality control engineer, and he would do these little tests for pH levels and stuff to kind of make sure it's within the kind of strict tolerance levels for the thing. And he kept and he was using like the normal distribution at the time to kind of do his estimates. And he would say, okay, you know what? I think something's wrong with this batch. We gotta throw this out. But then before they did that, they would do further tests, and then it'd say, no, it's actually still within range. It's like close to the limit, but it's still within range. So he's like, why does this keep happening? And he realized the problem is he didn't know sigma. He was using S as a thing, and so he kind of teamed up with a friend, a mathematician, and then they developed the T distribution. But Guinness Brewery, and he wanted to publish his results. Guinness Brewery didn't want him to use his real name because they didn't want to be associated with like academic journal stuff, and so he had to publish under the name a student, a pseudonym. So it came to be known as Student's T distribution. But anyway. Side note there, right? So that's what we did there, right? So that's the confidence interval, and then kind of probably the other big thing you learned in your intro stats class is just doing a hypothesis test, like a t-test or something like that, right? And so when we do a hypothesis test, we state some kind of hypotheses, and we imagine what does the world look like if this hypothesis were true, right? So we imagine this hypothetical scenario, right? We say, let's imagine this to be the case, right? And this hypothetical population, will have some kind of hypothetical mean and standard deviation. And we say, all right, if that was what the world looked like, what kind of values would we get, right? And does the values that I observe, or do the values I observe kind of align with this imaginary scenario? Or is there like a stark contrast, right? And so, you have different, theories about stuff, and we say, okay, does the data I have, does that align with the kind of hypotheses or not, right? So, you think back to the times of antiquity, and they said, well, one proposal for the way the universe works is, the Earth is at the center, and we see, stars going around, and everything's kind of revolving. And they said, okay, well, if that were the case, how do you explain, the movement that we see in the planets? And they had, different explanations for that. And then, later on they said, okay, well, what if we changed it from the Earth being the center to the sun being the center, right? And then we say, all right, if this were the case, if the sun were the center, and the planets went around in a circle, what would we see? And then we said, oh, you know what? The data actually kind of align a little bit better, but they're just a little bit off. And then they say, okay, well, what if we said the sun was the center, but they went around in ellipses, right? And then we said, oh, you know what? The data align with that hypothesis a little bit more. And that kind of, we had support for these theories. So similarly, we do something, at a much more like basic level. We just say, all right, in this imaginary scenario, let's imagine our null hypothesis says the population has this mean, and these are the values that I've observed. Do the values I observe kind of align with this idea that the population has this mean, or are they quite different, right? So let's say we wanted to compare two populations, okay? And we want to do this t-test to compare these two populations, right? So our null hypothesis is going to be something like this. Here's population 1 and here's population 2. And our null hypothesis is that these two populations have the same population mean, that there's no real difference between the mean of these two populations. And we say, well, if that were the case, right, in this imaginary or hypothetical situation, population 1 and population 2 have the same mean. When I take a random sample from population 1, I'm going to get a sample. When I take a sample from population 2, I'm going to get another sample. And if the two populations have the same mean, I would expect my two samples to have means that are quite similar. Okay. Now, I also understand there's random sampling. Therefore, they're not going to be exactly the same. But I would be surprised if, sample 2 had a mean that's like 5 times bigger than sample 1's thing, right? Because that does not quite align with the idea that the two populations have the same mean. So I look at my two samples, and then I ask this question. Could the samples I get have just been drawn by random chance? Or is it like very unlikely for this to happen? Okay? And we calculate this p-value, okay? The p-value is the probability of getting basically the data in our sample, observing our data, or something more unusual, more extreme, if we assume that the null hypothesis were true. And so that's what we're going to say, right? So when we take a random sample from each population, we expect both of the samples to have sample means that are approximately equal, right? So overall, we would expect the sample means to have a difference of 0. Probably, when we look at our data, they're not going to have the exact same sample mean. X bar 1 and X bar 2 are going to be a little bit different, right? And we want to know, okay, let's say X bar 1, did I use values? Okay, let's say X bar 1 has a mean of 10 and X bar 2 has a mean of 12.5, okay? And so the question is that difference between 10 and 12.5, is that a significant difference? Or is this difference possible from just kind of random sampling, right? Is it possible that population 1 and population 2 actually have the same mean in the population, but just by random sampling, we happen to get a mu that was a little bit lower, like around 10, and we got, or X bar that was like 10, and X bar 2 ended up at 12.5. And the answer is, well, maybe it really depends on the standard error, right? It depends how much variation, right? If all of the values in sample 1 were like really close to 10, 9.9, 10, 10.1, 9.8, 9.9, 10.2, 10.0, things like that, and then all the values in sample 2 were very close to 12.5, right? 12.5, 12.3, 12.4, 12.6, very little variation there. It would be hard to believe that these two populations have the same mean, and just kind of by random chance we got, all of these values really closely centered around 12.5 and all these values really closely around 10. Okay. On the other hand, if there's quite a bit of variation, right? Sample 1 goes from like 6, 10, 16, 15, 12, 3, and you take the average of all of these things, you get an average of 10. And then, population 2 also have similar values, 6, 12, 13, 20, 20 or whatever. But overall, the average happens to be 12.5. Then it's more believable that the two populations are similar, and just kind of by random coincidence, you got these things, right? So it really depends on the standard error. And so one scenario is that the standard error is very small, and that difference of 2.5 between 10 and 12.5, we have a difference of 2.5, is much larger than, say, the standard error that we see, okay? And we would say that this difference of 2.5 is significant. On the other hand, if within your samples you have a large variation, lots of big standard error, this difference of 2.5 is not significant, okay? And so we do that and we calculate p-values, right? So the p-value is, what's the probability of observing our data or something more extreme, more unusual if we assume the null hypothesis were true? And, your quick conclusions are, if the p-value ends up being small, meaning that getting this difference of 2.5 is really unlikely, right? If the null hypothesis were true, this is what the world looks like. Is it possible to get a difference of 2.5? Maybe. It's not. We hate to use the word impossible in statistics, right? statisticians never like to use the word impossible, but getting a difference of 2.5 seems really, 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 really unlikely, right? It's kind of like, if I have a fair coin, could I flip the fair coin 20 times and get 19 heads out of 20? Could that happen? It's possible, but it seems really, really unlikely, right? So how do you explain the fact that you got 19 heads out of 20? Well, it's much easier to say, rather than I got this really, really, really lucky scenario, it's much easier to just say, you know what, I think something's wrong with the way you're flipping the coin, or something's wrong with the coin itself. And that's an easier explanation for how we got 19 heads out of 20. So similarly, we can say, how do we get this difference of 2.5? Well, the p-value is really small. The easiest explanation is that the null hypothesis is wrong. That you know, if the null hypothesis were true, we shouldn't be seeing a difference of 2.5. We got a difference of 2.5. How do you explain that? Probably that null hypothesis is wrong. Okay. On the other hand, let's say the p-value is large, and so our data is not a weird thing to happen. Okay. And so we would say, you know, I have no reason. We do not reject the null hypothesis. It's kind of like flipping a coin 20 times, and you get 11 heads out of 20, okay? 11 heads out of 20, that's not exactly the same as 50-50. We didn't get exactly 50% heads and 50% tails, but then 11 heads out of 20 is not weird, okay? We'd say, oh yeah, you know, that could happen just by random chance. And so we're gonna say, you know what? I don't have any reason to doubt that this is a fair coin and I'm flipping the coin in a regular manner. Now, is it possible that this is actually an unfair coin? You know, maybe slightly biased to give me more heads than tails? It could be. It could be, right? But, you know, I just don't have enough data to say either way. So all we can say is this, no reason to reject the null hypothesis. All right, and so that was kind of probably where you got through in your intro stats class. Maybe you also did like chi-square tests and, you know, some linear regression and things like that. But all of those things basically were centered around the central limit theorem, right? And you proved that in your stats 100B and things like that. And where we are going to go next week, okay, is we're going to do something called randomization tests. And I don't know, some of you might have done randomization tests in your intro stats class, but usually it's not something. So, well, I don't know. What did they say to do if like the central limit theorem doesn't apply? Was it just like, we can't do this test or something like that? That's often kind of where I leave it at stats 10. When I teach stats 10, we'll say, you know, check your conditions to see if the central limit theorem applies. And if it doesn't apply, then you just have to back off and say, you know, we can't do the test right now. Okay. We're going to do something next week. We're going to use the computational power of the computer to do this randomizing stuff. And we're going to do something called a randomization test, right? And we're going to test some similar kinds of things, like the null hypothesis that there's no difference between the group means. But rather than depending on the central limit theorem, we're going to use randomization. And we're going to say, what if, you know, I can't assume that this follows a normal distribution, but what I can do is I can kind of simulate what my sampling distribution looks like, right? So over here, I generated a sampling distribution. We're going to do something kind of similar. We're going to say, what could happen by random chance, right? What kind of results could we get by random chance? How does that compare to the results that I see? So that's where we're going to go next week, okay? I've got just a couple minutes left. This is kind of just a review on data collection, and I think it's okay to just say, hey, read these slides on your own time. But basically, we have random sampling and we have randomization, okay? Or random assignment of treatments. And the implications of what you can do and what kind of conclusions you can make depend on whether random sampling was used or whether randomization was used, right? And so I've listed off basically 4 kinds of scenarios, and one, you know, basically one where there was no random sampling, one where there is no random assignment, okay, one with no random sampling but with random assignment, one with random sampling but no random assignment, and one with both random sampling and random assignment. In reality, it's hard to kind of get both. This one, basically, with appointments in the first 2 weeks in December, this is not random sample. And then those who normally take vitamin C and those who do not, so no random assignment of treatments. And basically, when you have something like this, no random sampling, no random assignment, then you have an observational study and you don't have a random sample. So if you don't have a random sample, you can't generalize to a larger population. And if you don't have randomization, you can't make any kind of cause and effect conclusions, all right? If you want to, if you have random sampling, then you can generalize to a bigger population. When you have random assignment, you can make cause and effect conclusions. And the scenario 4 is kind of this fictional fantasy scenario, the statistician's dream scenario, but not actually possible, is having random sampling and random assignment. And in reality, it's almost impossible to have both random samples and random assignment, because in order to do random assignment, you need like patient consent to participate in this thing. And as soon as somebody says, I don't want to participate, it's no longer a random sample, right? And so this almost never happens in real life. But just imagine if you did have a random sample and random assignment, then you could generalize and draw cause and effect conclusions. But yeah, in reality, that's not really the case. And running a true random experiment is like really hard to do in real life, because have you taken 101B? Are you taking it right now? No. Do you have like a group project in 101B where you're doing an experiment? Maybe not. Okay, well, anyway. It's called design of experiments, right? Okay, I just want to check. So when you actually try to run an experiment, it's like so painful, and it's hard. It's hard. And so a lot of times, if in 101B, if you do have to do an experiment, how much data are you going to collect? You might be lucky to get like 50 observations, and that 50 observations might represent hours of labor, and that's often what ends up happening. So this is a side note again. I'm always going off on different tangents. There's kind of statistics like 101B and 101A kind of come from this era of classical statistics where data was expensive to obtain, right? So you think of like medical studies. Every observation, every patient that participates in your medical study is very expensive to get. Oh, let me give you your last view quiz answer. Last view quiz answer is B. B as in bear. B. And so 101B, ANOVA, design of experiments, is designed to maximize the kind of conclusions, make your test as powerful as possible using a small amount of data. And then on the other hand, we're kind of in this modern era of statistics. You have all of this like data coming from computers and like internet servers that just log every single click, and you have like hundreds and thousands or millions of records, right? And that comes with its own host of problems and complexities to deal with. And so you have a lot of these data mining and machine learning things where, like these classical methods just don't really work so well for these huge data sets where randomization and random sampling doesn't really apply anymore. So you kind of have different directions that you can head in for statistics. Somewhere where data collection is hard, data is expensive, you only have a few observations. You want to maximize the information you can get over there, and I would say that's kind of like 101B, and on the other hand, 101C is kind of more on this side where you have like huge amounts of data available. Okay, and 101A regression is like super applicable in kind of either scenario, although it probably fits a little bit better on the classical side, where with machine learning we have techniques that are a little bit more advanced and more capable as far as prediction goes, but not so much for inference. But anyway, okay, we'll go ahead and end there. Have a great weekend, and we will see you on Monday.